This is decision 2 from 2020. Let's just do it. So question number 1 is about the Hungarian algorithm. So firstly, we're being asked to maximize here total profit. Now, Hungarian algorithm minimizes stuff. So how do we get this to work? Well, what we do is we take the biggest number in this table, and we take that number and we take away every entry in the table from it to give us a new table. So for example, 35 is the biggest here, 35 minus 29 is this, 35 minus 20 is this, and so on. We'll skip these two for now. And we got all these. Now, what that's done is it's made all the numbers that were biggest, like this 35 and this 34, and it's made them the smallest, and all the numbers that were smallest, biggest. And what that means is, if I aim to minimize this table, which is what Hungarian algorithm does, I'll be maximizing the answer to this one as well. So cool, we've done that. We've got these missing entries. What we're going to do is we're going to slap in some 100s in there, and we'll just do the algorithm normally. So the algorithm will not want to pick these two because they're so big, they're so much bigger than anything else. So we can just do this. We'll get away with it. It'll be fine. So that's just from here. So reduce rows. Smallest in this row is 6. Take that away from everything. Smallest in this one is 3. Take that away. Take 0 away from everything there, I guess, and take 4 away from everything here. And then columns, take 0 away from everything there, and then 0, and then take 1 away, and then take 1 away again. And we get this. This will be what we work with. I think I can cover up all of these zeros in 3 lines. The fact that I can cover up all the zeros in 3 lines, where this is a 4x4 grid, means that it's not optimal. So what I need to do is I need to make another 0. So we look at all the things that are not covered, and we take away the smallest. So let's take away 2 from all of these elements, and we'll add 2 into the ones that are double crossed, like these two, and the others will just be left alone. And we'll make this table here. So these two have gone up by 2. All of these have gone down by 2, which creates another 0 for me, and all the others have been left alone. I think now it does take me 4 lines to cross all these zeros out, no matter how I do it, which means it's optimal. And therefore, we can just sit here and think of the way to make this work. The only person who can do 4 optimally is D, so he'll do that. The only person who can do 3 optimally is C, so they'll do that. The only person who can do 1 optimally is A, and therefore B does number 2. Determine the profit, well, D4 is 30, and then C3 is 34, so we add those two, we add this, and we add this, and we get our total profit of that. First question down. Question 2 is the decision tree correct problem. So, okay, to find this circle here, we do this times this plus this times this, which is, should be a closed bracket there, but that's okay. And then this times this plus this times this gives us this one, and then this times this plus this times this gives us this one. We're looking for the highest, of course, which is this one. So if she chooses option A, her EMV is 154, and that's what we'll do. But now, however, we say that we've actually got a utility function with the money, so the money doesn't just go up linearly. It follows this function here. So what we can do, I think I was probably a bit lazy here. What I literally just did was I shoved 350 into the utility function, times it by 0.6, and then added what happened when I put 140 into the utility function, or actually minus 140 times by 0.4, and that just gave me this EMV here. Maybe you want to be a bit more, just to pick up all the marks. I'm not 100% sure, but you might just want to put the utility function of 350 here, and then this same for this one, and then times it by these two and add them together. I don't know, but this probably earns 4 marks. Do the same thing for the next one, and the same thing for the next one, and we end up with the answer of option B having the highest utility at about 0.206. Okay, question number 3 then is the transportation problem. Notice how I'm saying it's the transportation problem, because in decision 2, there are there are usually 7 questions, and you'll get transportation, you'll get Hungarian, you'll get decision tree, like we've seen. You'll get game theory, you'll get recurrence relation, and so what's the final problem? Dynamic programming. Like, you'll just get all of those. So these are just the questions we'll see on these. So this is the transportation problem. Northwest corridor has been started here. So what we'll do is they've told us to start at AR, so let's just slam in a theta into AR, which of course means decreasing this by theta to make this row still add up to 42, means increasing something here by theta, and we've already got the 17 to increase, so that makes this one still add up to 59. We need to decrease something here now, so we'll decrease this one by theta, again to make it match up, and then we need to increase something here, again to keep them balanced, and then finally decrease one here, and I think now this, and this are all balanced, so the 40 can just chill out and just be a 40. And what we're going to do is we're going to choose the biggest theta to make all these positive, which will be 4. So we'll choose theta to be 4, and that one keeps this one at 0 rather than being negative, and we get this table. And yeah, that's our first iteration. And now it wants us to do it again. So we're going to do the shadow costs first. So what I do is I just put in the costs of the routes that we're using in here. We're not really using this one. I should have just got rid of this 0, but put the cost of the roots that we're using in here. Usually you see X is written here, but I just like to put the numbers in red. And then we're going to start putting shadows in. So 0 here, we'll start with always put 25 here, because these two need to add up to make this one. So this one needs to be minus 18, because these two need to add to make that one, which makes this one a 30, I think, because those need to add up to 12. That makes a 17 over here, which I could write down, but I've also just gone straight to here next. That makes 17 there, and then that means to be minus 4. And then to find these improvement indices, you do what's back here, 13, take away this, which will of course be adding in. We'll get that. Here we'll do 16, take away this, which we'll be adding as well. 16 take 25 is minus 9, plus 4 is minus 5. We'll do the same thing for all of the remaining boxes. And now we've got some negatives in here, negative improvement indices, which means this is not an optimal solution. We'll take the biggest negative improvement indice, which is minus 11, and we'll replace that with a theta back in this table, and we'll do the same thing from here as we did previously. So what we'll do is we'll replace, well, we need to balance out this theta, don't we? So the row we'll sort out first. We'll need to replace that 40 with a 40 minus theta, and then the column we can balance now. That 4 needs to become a 4 plus theta to balance this. Then this row here, that needs to be a 38 minus theta, balance here to make it a plus theta. And not everything's quite balanced. This one isn't yet, so we'll make that a 47 minus theta. And now I think rows and columns are all balanced. So this 25 is okay to just stay as a 25. We can choose theta to be 38, I think, and keep all of these positive. So that gives you this. I've just replaced everything, theta with a 38 and substituted. I can write down here the entering cell, just because they asked for it. The entering cell is the one you put theta in, that's DQ, and the exiting is the one that goes to 0, which is AP. And yeah, so this is my improved thing here. And I think it says determine whether the solution is optimal. So again, same thing here. So I put the costs of the roots that I'm using over here. I'm going to do some shadows. So start with 0 here. Even if this is missing, you can go to a 17 there then. And then this will be a minus 4 to make those add up. This will be a 19, I believe, to make those add up. Now you can get these two, because you can do 19 and these two. And you'll get these numbers here. And then, of course, this needs to be a 14. And then we can do the improvement indices. So this minus this minus this, and then this minus this minus this, and so on. Do that for all of them. And we get all positives, so no negative improvement indices means everything is good to go. It is optimal, and we're good to get this done. Next it says formulate this as a linear programming problem. So must define some variables. So we'll start with xij, and we'll let xij represent the stock delivered from supply point I, which can belong to either, or can take the form of A, B, C, or D, to sales point j, which can be P, Q, or R. And we're trying to minimize 25 times how much goes along this route. So we're trying to minimize 25 times xap, plus 24 times xaq, plus 17 times xar, and so on. Just reading all the way through the table, we're trying to minimize all of that. And the constraints, of course, is that anything that comes from A has to add up to at most 42. So x, so you can represent this with a sum, but the sum, so xap plus xaq plus xar must be 42 or less, which in our optimal solution it is 42, isn't it? You can probably get away with writing equals here, but cool. So we have this, because it's a balanced problem, I think equals would be fine. Then we do the same for the B's, the same for the C's, and the same for the D's going across, reading their numbers. And then also, the opposite idea, the stuff that goes to P from all these places has to be at least 59. So it can be greater than, again, you can probably get away with equals there, but it has to be greater than or equal to 9, and that's the sum of everything going to P. So the sum of x AP plus BP plus CP plus DP and so on. So all of those, and likewise for the Q and the R. And I think that's all we need to say. I would just make sure you've done that a couple of times so you can pick up. It's a lot of marks to lose if you're not sure what to do. Explain why simplex can't be used. So standard simplex can't be used when you're using greater than symbols. So yeah, just jot that down from D1. You could use two-step or you could use big M method, but sure. The recurrence relation question then, so so we've got this thing is given by this thing, find alpha and beta. So we'll look for the auxiliary function, which is just this thing here, m squared plus alpha m plus beta is 0. Now, you know what happens when you solve this. You get 2 and minus 1 as solutions, which means this must factorize to m minus 2, m plus 1, because that would give a solution of 2, which would go there, and that one would give minus 1. And of course, they're 2 real solutions, so it's of the form this. Of course, we can just expand this out, and we can notice alpha is minus 1 and beta is minus 2. And we have this, so that's good to go. Next, if we're going to solve this properly, we need to think about the particular bit, so this bit here. So we'll just set un to equal lambda minus 3 to the power n to start with. And now, of course, that makes un plus 2 equal to lambda minus 3 to the power n plus 2. It makes un plus 1, and remember, alpha is minus 1, so that's just there. But un plus 1 is just lambda minus 3 to the power n plus 1. And then this is just lambda n here, with this minus 2 as beta that we had before. And that equals all of this. Of course, this here you can write as minus 3 to the n times minus 3 to the 2, because you'd add these powers up to get this. And of course, minus 3 squared is just 9. And same trick over here, minus 3 to the 1 is just minus 3. So this actually becomes a positive there, I think, just positive 3 lambda. And likewise, this all just stays the same. But now you can just divide by minus 3 to the n, and you just see that 9 lambda plus 3 lambda, which is 12 lambda, minus 2 lambda is 10 lambda, equals 20. And so lambda is 2. So we'll have our solution as this bit plus 2 minus 3 to the n. And now they've given us some stuff here we can use. So u0 is just what happens when you put zeros in here. Of course, all these zeros just become ones, essentially, so we get this. u1 is what happens when you put 1 into here, and that's equal to this, except it's told you that 2 lots of this one is equal to this one. So we can do that, and we can actually solve for b straight away. And then we can look at the last condition here. u4 is this, so we put in 4. u4 is 164, so that replaces with a 164 as well. We get all this. And then, of course, you can put b into here and solve for a, and you end up with this. And then you can just write out your solution like this, and you'll be done. Excellent. Question number 5 then is the flow question. Yeah, I missed that from this, and I listed 6 things earlier. There are 7 things. There's a flow thing is the last thing that you're always asked to do. So yeah, the source node is the one that stuff is coming from. That's clearly C, free mark. Sink node is G because everything's going towards it. The capacity of C1. Now this is a little bit dodgy just because it goes in such a wild path. But the idea is, imagine you were to kind of lay this out in a line and think about which ones are going upwards and which ones are going downwards. And like the ones going upwards are going towards G. So we add those in. So we take 10, we take the maximals of the ones going towards G. So it's 10 plus 2, both of those are going towards G. Again, if this was lined out, this one is going downwards. So we'd use a minus 1. You'd use the minimum for the ones going the wrong way, down into C. So this is going down, even though you think, oh, it's going to G, but like everything's going to G, so that doesn't matter. It's going downwards to the part of the graph where C is, underneath the line. So we use the minus 1 because it's going the wrong way, and we use minimums where it's going the wrong way. So it's 10 because that's going the right way, plus 2, both maximums because they're going the right way, minus this 1, and then plus this 6 because that would be going upwards if you laid this out in a line. So plus 6. This would also be going upwards, so plus 8, minus this 1 here because it's going downwards, and then this would be going downwards as well, because if you lay this out, if you pull it all the way out and lay it down, this will be going downwards as well, wouldn't it? So this will be a minus 0 at the end. So quite easy to make a mistake there, but you get 26 in the end. Assuming a feasible flow exists, explain why JH must be at upper capacity. Find JH, it's here. Look at JH, it's got a maximum of 5, and the minimum going into it is 3 and 2. So at minimum, 5 is going in, which means at maximum must be going out. Explain why AD and CD must be at lower. So AD is here, CD is here. Again, look at D. Its maximum going out is 9, and AD and CD minimums going in make 9. So therefore, they must be at their minimums, because otherwise D would be over capacity there, and nothing could leave it. Use diagram 1 to show a flow of 18. Now here, just take all the information they've given you to start with. So we know, for instance, that JH must be a maximum, so we can fill that in, which means these two are at minimums. And then the next bit we learned was that this is also at maximum, which means these two are at minimums. So we can start there. So we have quite a good start here to go with. And then we just fill in the rest of it. Like this 1, for instance, that has to be a 1 because there's nothing else it can be. It's 1 or 1. And then here, well, you've only got 1 coming into B, so only 1 can be leaving it. But the min here is 1, and the min here is 0, so that must be 1 and 0. That makes sense then. And then you can sort out C because there's only 1 thing going to that's missing from node A, so that must be a 4. 1 plus 4 is 5. Then we've got a little bit more sorting out to do. I can't remember what I thought to do next. I put a 6 here. Why have I done that? Well, because, and let me very quickly work it out on the fly. There's 2 more units leaving F than there are currently entering it. So essentially, this one here needs to be 2 less than whatever's in here. I think it's my logic. Sorry, 2 more. Sorry, 2 more than whatever's in here. Because 6 plus 0 has to equal something plus 2, or whatever's in here is something plus 2. But the least this can be is 4. So even if I made this minimal 4, this would have to be a 6. If this was a 5, this would have to be a 7, which can't happen. So 6 and 4 is the only thing that works here. You know the maximum flow, the flow that you're searching for is 18. So that means the flow out of C is 18. So we just have a 3 left, just do 18 minus the other ones. So if that's a 3, we can sort out these last two. There's only a couple of arcs left, so you just find a thing that works. And eventually you get this. This is the only thing that works because, I mean, you can't put a 0 here because then you'd have to put a 6 here. And if you put a 6 here, that would have to be 11, and that doesn't work. You can't put a 2 here for similar reasons. I think, well, why can't you put a 2 here? Because that would have to be a 4, which it can't be, right? So, cool. So that's the only thing that works, I think. Prove the answer E is maximum flow through the system. This is essentially just asking you whenever you're asked to do a proof in a flow question, you're asked to find a cut. So what we need to do is we need to find a cut of flow 18, because then by the maximal flow minimal cut theorem, if we can find a cut of flow 18, that means the maximum flow is 18. So we just need to find a cut in this original system of flow 18, and get your calculator out and just get ready to do a bunch of sums and try and find something. Eventually you'll find this. Again, flowing left to right will add, flowing right to left will take away. So here we've got 7 plus 2 plus 3 plus 6 plus 1 and then minus 1 because that one's flowing the other way and because we take away the negative. And when you do that, you end up with 18, I think. And so that's by maximum flow minimum cut theorem is going to be our maximum flow. So only 2 questions left. We've got the game theory question here. Why can this be reduced to 3 by 3? This is a domination question, right? You look for a row here. You know it's going to be a row because there are more rows than columns. Look for a row that's dominated by another row. So I think we can find S. From player A's point of view, everything in S is worse than everything in T. You only win 2 here rather than 3. You lose 4 here rather than just losing 2. And you lose 2 here rather than breaking even. So you never want to play S, right? Playing T, regardless of what what player B plays, is just better. So it's dominated. You need to use the word dominated. Verified there is no stable solution. So we'll get the minimums out down here. So the worst thing that can happen if he plays Q is he only wins 1. The worst thing that can happen if he plays R is he loses 3. And the worst thing that happens if he plays T is he loses 2. And the best of these cases is this one here. So he's going to play option Q from a play safe point of view, because the worst thing that happens is he gains £1 each time, or 1 whatever. For B, exact opposite. So you're thinking about this. This is losing 4 for player B. This is losing 3. This is losing 1. So the worst case is losing 4. Worst case here is losing 5. And the worst case here is losing 3. The best of those is Z. He'll choose Z from a play safe point of view because it only loses 3. And because this 3 isn't equal to this 1, therefore there's no stable solution. So those values aren't equal. If they were both equal to each other, then we have a stable solution, but they're not. So we model this in some linear programming. We get all these numbers. Now, the first thing to mention, and this will come up later, is where does this 4, 7, and 6 come from? Because you definitely can't see in these tables. But when you're modeling the simplex algorithm, you can't have any negatives in the table. So what they've done is they've added 3 to every single. They've obviously ignored this, so the -4 here doesn't matter. They've added 3 to every single value in this table, which means, of course, at the end, when we work out some amounts, we'll take away 3 at the end. And when you add 3 to every amount, this becomes a 4, a 7, and a 6. And that's where those numbers come from, because what this is talking about is it's the payout if player B chooses X. There's 4 times P1 plus 7 times P2 plus 6 times P3. And that's what that payout is talking about. And the same thing for the other ones here. So that's what they've done to get those. Explain why it can't exceed any of these. Now, I've done something unusual for me. I've just copied the mark scheme. So this is what the mark scheme said. So you had to essentially find some way of saying that when we get the P's, which we will do at the end, we'll work out what all these V's are and we'll choose the minimum one. And that's why these signs are less than and why we can't exceed any of them. Is because, like it says here, we just need to show an understanding that we'll seek the minimum one. Once we put the P's in, we'll seek the minimum one, and V can't be bigger than this. So that's why we always use these less than signs here. Explain why it's necessary to use this constraint. Again, this is what the mark scheme says this time. You just need to get across the point that when you're using simplex, you need to be able to pivot around this row if you need to. So that's why it's less than, and we'll use a slack variable in there. So some implying that we need to be able to use simplex is enough to get the mark there. They are only 1 mark each, so just these B ones will do. Anyway, now that we use simplex, we have the optimal solutions. P1 is this, P3 is this, and therefore, of course, P2 is 4/11 because those are the only 3 things that player A is going to do. Calculate the value of the game for A. So this is exactly what I'm talking about here. We're going to put in 7/11 times 4 plus 4/11 times 7 plus 6 times 0, and we'll get this. We're going to do the same thing here. 8 times 7/11 plus 4/11 gives us this, and the last one gives us that. And we're choosing the minimum, which is either one of these two. It doesn't matter, but we need to choose the minimum because we're less than, as we were saying up here. But of course, we've added 3 to this entire game to make it all positive, or 0. So we're going to take away 3 from this to get our final thing of 23 over 11 as our answer. Player B intends to make a random choice with property Q1, Q2, and Q3. Now, there's a couple of ways of doing this. So essentially, we're being asked to find Q1, Q2, and Q3. A couple of ways of doing this. The first thing to note is that player A is not going to pick option T, because you're told that the probability for that is 0. So all we need to do now is we can say, well, okay, if player A picks Q, player B's winnings are 1 times Q1 plus 5 times Q2 plus 3 times Q3. And we know player B's winnings are the same as the winnings for A. Now, they're not. Player B's winnings are actually minus 23 over 11, but I've actually stopped doing this table in reverse, haven't I? Like, player B's winnings are actually -1 and -5 and -3, because it's the opposite from his point of view. But if you just put minuses here with a minus 23 over 11 there, then they would all cancel anyway. So I can just completely ignore that now. I can just put the 23 over 11 here and treat these as positives. Now, you'll also notice I haven't bothered to add 3 to any of these numbers anymore, and that's because I'm not doing simplex algorithm. I'm just substituting in results, so I don't need to. So the next one, if player A chooses R, is just 4 times Q1 minus 3 times Q2 plus Q3. And the last thing we know is, and that must make the same value, of course, and the last thing that we know is that Q1 plus Q2 plus Q3 is equal to 1. And that's just a three variable simultaneous equation, which you can put in a calculator and you can get these answers here. There is an alternative way of doing it, just in case you weren't happy with that, which is, from this down here, this V here is the winnings for A if B chooses Z, right? So if B chooses Z, then it was, add 3 to these, it was 6, 4, and 3 here. This one's not relevant. Now that's bigger than these two. So what that's telling player B is that player B should not play option Z, because his winnings will be worse than if he plays, or his losings really, will be worse than if he plays option X or Y. So actually, from this information here, we can just learn that PQ3, his probability of playing Z should be 0. And then we can just set up a nice 2 simultaneous equation, whereby these winnings equal these winnings, or you can just set these equal to the 23 over 11, and you can just solve, but you can also just set this equal to that. Thinking about this, like, do you remember that chapter in the textbook where you had to draw graphs of these things and you had to find the intersection? Well, I'm not drawing the graphs because I can't bother, but I'm just finding the intersection between this payout and this payout, because that will be the optimum place. And of course, I can use the information that Q1 equals Q2, Q1 plus Q2 is equal to 1, because I know that one's 0, to substitute that in, and I'll find Q1 is this and Q2 is that, which is the same as I found. I believe it is at least the same as what I found earlier. And maybe just write down at the end here. The optimum strategy is to play X with 8/11, Y with property 3/11, and never play Z. It's just probably what you have to write down for the last mark. Okay, so question number 7 is the dynamic programming question. There are 3 types of dynamic programming that exist, I think, in D2 exams. Or when I say 3 types, they always ask you this table, and they always bang out a load of marks for it. And there's this one, what we're about to do. There's the one where you have to build a certain number of things to order, and there are constraints that involve the building. And then there's the one that uses the graphs. I would highly suggest that you know roughly how to do each one of those 3 things, because this is a lot of marks to lose if you're not sure how to get this table going for any one of them. So okay, they've started you off, which is good. So we'll keep with trainers. This starts off really boring. I'll probably just define these things first. State is the shoe wear that we're considering. State is the number of units that we're going to be making available. This will become more clear, I think, in a second. Action is how many of those particular units that I've got here that we'll be taking. And destination is the units that are left, the number of units that need to be filled with previous things. So that probably doesn't make any sense too much, but I'll try and explain what's going on as we fill the table. The first fills in are really, really, really pointless. We have 1 pair of trainers. The only shoes we're considering are trainers, so we'll just take those trainers, and we don't have any other shoes to consider, and 1 pair of trainers is 50. 2 trainers, we have 2 trainers, there's no other shoes going on, it's going to be profit 90, and so on, 3, 4, and 5. So that's really boring. We just have to start there anyway. Then we consider the sandals, and this is where this whole dynamic programming comes in. What we'll do is we'll say, okay, let's just pretend we're only selling or shipping 1 pair of shoes. If those are the sandals, we'll make £70, or in thousands, so 70,000, but it doesn't really matter. But we could not make those as sandals. We could make them instead the things that we were considering earlier, which are trainers. and in that case we'd make 50. And now the best thing to do here is to make sandals, and because that's the and I'll put a star on that to denote that. Now the reason that we're doing this, of course, is because when we get all the way to high heels, what we'll consider is, oh, what if we made 4 pairs of high heels? What's the best shoe to pair up as our 5th option? Well, that will be this one here. And we'll go back to this and we'll see it. And likewise for 2, 3, 4, and so on. So hopefully this will be more clear as we go through. So if we have 2 shoes, we could do 2 sandals, which would be 110, and no trainers, which would be 0, obviously. But we could do 1 sandals, 1 trainer, or 0 sandals, 2 trainers. So 1 sandal, 1 trainer is 70 plus 50, which is 120, which is better than this option. And 0 sandals, 2 trainers is 90, which is worse. So if we ever have to get 2 pairs of shoes, currently the best idea is to do trainers and sandals, 1 of each. Then for 3, same kind of idea goes on here. You can either do 3 and 0, 2 and 1, 1 and 2, or 0 and 3. We'll find all the profits for those. So 3 and 0 is 165 and 0. 2 and 1 is 90, is 110 and 50, and so on. The best choice here is 0 sandals and 3 trainers is the best choice for 3 pairs. Then we go to 4 pairs and do exactly the same thing. And again, this will all come together at the very end, really. But exactly the same thing for 4 pairs, just listing all out super systematically. We'll go on to 5 pairs now. So 5 pairs is the most to do, but it's okay. It's just the same thing over and over again. So this is 5 pairs of sandals, no trainers, 4 sandals, 1 trainer. Just look in the table for the numbers, and we'll get all these. We'll find the best one, which is this one here. 5 sandals this time, no trainers. And this is where it all comes together, because now we start considering high heels, and we're like, okay, what if we, firstly, we're going to use 5 things. We want 5 things in total, because that's going to be more money than if we only have 4. We have 5 to ship, so we'll do 5. Now, what if those 5 things are made up of 5 high heels and 0 anything else? Or 4 high heels, 1 of something else. So not 1 trainer specifically, but 1 of something else. And then 3 and 2, 2 and 3, 1 and 4, and 0 and 5. Well, 5 and 0, 5 high heels is 3 or 5. And then we're not making anything else because we got 0 here, so that's 3 or 5. 4 high heels, and then we need to find what's the best way of making 1 of something. So we go to state 1, and we find the star. That's 70. And so 4 high heels is 3, 2, 3, 5. Add the 70, get 3 or 5. Then what if we do 3 high heels? Well, that's X. And then the best way to do 2 of something else is this one here. That's 120. So the answer will be X plus 120. The next 2 high heels is 115. And 3 of something else is, the best thing is this one here, 170. So we add those together. 5, 1 high heel, 4 something else. So 1 high heel is 75. 4 of something else, the best option is this one here, 245. And then finally 0 and 5. The best option for 5 of something else is this one here, 5 and 0 here. So okay, we have all of this. The best options, well, we don't really know what the best option is. It depends on what X is. The best option is either this option here, 320, or X plus 20, depending on what X is. And that will be that done. And then it says the maximum profit is this, which, thinking about it, I never used, which means maybe I've got the last question wrong, because I absolutely haven't done that. But, yeah, is that relevant? I don't know. Anyway, oh no, wait, that just means this. What have I? No, it doesn't, because you could make X 200,000. Oh, so it could mean either of these 2 things. Okay, well, whatever. Explain the possible ways. So if you do the 320, all I did was I assumed that either one of these things could be the case, because it says possible ways. If you do 320, going back along this solution, so 320, I should have put a star here, but it doesn't really matter. Or maybe I shouldn't. It doesn't. Yeah, it doesn't matter. If you go 320, that involves making 1 pair of high heels. So 1 pair of high heels. Go back to the 4 one. And the best option for 4 was to do 4 sandals and 0 trainers. So that's where this comes from. So that's the way to do it if that's the maximum option. If this is the maximum option, you want 3 high heels, and then you find the 2 option, and the best one for that is 1 sandal and 1 trainer, going back here. And so that will be what you suggest they make. I think that's it done. Thanks for watching, and I'll see you next time.